Hello everyone. Today's lecture is Projective and Injective module. Projective and Injective module is also type of the module, more complicated the property. But anyway, I will introduce the definition of Projective and Injective module and some examples and the properties of Projective and Injective module. Now let's talk about Projective and Injective module. Our first concept I introduced. This injective and projective is literally a module, but some definition is a little complicated than the module we already know. Let's read the definition. A module P over a ring R is said to be projective if given any diagram of R module homomorphism with, in this case, bottom, to compare to injective R module, bottom row exact. See, this is exact sequence, but note that we run that if this exact sequence is given, the map G A to B is epimorphism, or rather than in this case is better surjection. Okay, yeah, so if map G is surjection, then there exists R module homomorphism. In this case, map for convenience for H from P to A. What this mean? If you draw the commutative diagram, P is here, and this map exists, such that the diagram is commutative means we know that we can't go from P to B because the map is composed with composition. So for convenience, if we put in the map F, then F is composition H and G, and this map is commutative. So if this property holds, if P is a module, but this property is hold, then module P is called projective R module. Let's see the definition. Injective R module. A module J over a ring R is said to be injective if given any diagram of R module homomorphism in this with top row exact sequence. This is top. What is top? If we draw the diagram here, so relatively the exact sequence are located. This is top, this is low. In this case, but because this is an exact sequence, so if I put the from morphism A to B mapping homomorphism, R module homomorphism from A to B, put G is injection. So 1-to-1 map. Then there exists R module homomorphism. In this case, the row is opposite. So H, J to A. And what is diagram commutative? In this case, we can go from J to B with the commutative diagrams hold. So in this case, there exists R module homomorphism H such that F is composition H dot G. Okay, is this right? Okay, then the J module J is called injective R module. But if we know the concept of the category, which run in the lecture third in my clip, generalization of the concept projective object and injective object. As we learned, the concept of a category theory is generalization of the concept. For example, pre-R module and pre-abelian group is generalization of pre-object. Okay. In some sense, similarly, we can define projective and injective object, which is a generalization, projective and injective module. Let's read the definition. An object P in a category P, in this case, P, A and B are objects. It's projective for any epimorphism E, A to B. This is E, but if we deal with the projective object, the allow and zero set is not necessary. Just we know this exact sequence is epimorphism. Map E from A to B is clearly epimorphism. We know this result, this allow and zero set is not necessary. And note that this is just morphism, but epimorphism. But this is not a function, just morphism. And the morphism P to B, in this case P to B, then there exists morphism P to A. There exists morphism P to A such that the diagram is commutative. What's mean? From the definition, F is this morphism. Then commutative relation means F is composition H to E. So this commutative relation holds, then object P is projective. This is similar concept of projective module, but this is generalization. Similarly, we can define injective object. An object J in a category J is injective for any monomorphism MA to B. But we know this exact sequence in case of our module, because this map is a monomorphism, the zero set, and the also allow not necessary, and J is given, and consider morphism F J to B. Then there is a morphism J to A. In this case, there exists morphism H J to A such that the diagram is commutative. This means here. So the map F is composition HM. Then this object J is called injective object. Now let's see the example of projective and injective module. Practically speaking, it is hard to find which is injective or which is projective or injective if we just use the definition of the purely the definition. So in order to check whether it's projective or injective, we use some theorem or equivalence relations of projective, which is related projective or injective module. This example is the main theorem which to decide what is projective. Pre-module F over a ring with identity is absolutely projective modules. But I will not prove detailedly, but use the roughly the definition and the arrow. Let's see. This is the exact sequence. We know this is, if we put the map G, this is injective map. Okay. And consider the definition of pre-R module. Definition of pre-R module is we pull any R module that exists hold commutative relation such as this triangle commutative diagram holds. So if we just moved here, for any R module, we can construct this commutative diagram holds. So we can find this homomorphism exists because this universal property. So we can find homomorphism H such that commutative relation holds in the sense F. So clearly F is pre-module F is projective R module. Note that in general we pre-R module, but pre-module is the generation of pre-R module. Pre-module is generation of pre-R module, but I will not deal with in this lecture. I will not deal with the concept of pre-module. So consider pre-module as pre-R module in this slide. So anyway, pre-module F is projective module. Now let's consider the tool to decide the module is injective. In this case, we restrict to G module. So if in case of G module means G D to D. This is additive, clearly additive abelian group. And the tool which module is injective is here. The module is injective G module if and only if an abelian group D is divisible. What is the concept of divisible? The definition of divisible is here. First, choose for any element y in D. Then, for any arbitrary natural number, we can find x in itself such that y is mx. Then the group D is called abelian group D is called divisible. So the equivalence condition D is injective module is abelian group D is divisible. Let's see the concrete example. First, rational number Q is clearly injective Z module. Why? First, pick for A over B in Q, then for any n, we can find A over B is equal to, if A over B is equal to y and y, then we can find y always construct. Then, however, because n is natural number, y is equal to a over nb, and this is clearly rational number. So we can find for any rational number and for arbitrary natural number, we can find rational number y such that this formula holds. D is divisible. D is divisible, and by the theorem, D is injective Z module. Of course, the proof is I will omit the proof, but this tool is useful to check which is the G module. However, integer is clearly non-injective module. Why? Whatever. This is counterexample. Just we easily know. For example, let 5 is clearly integer and choose n is 8. Then our claim is to find y in G such that this is 5 is equal to 8 times y, but y is clearly exists. Y is rational number, but not the integer. So integer is non-injective G module. Let's see the split exact property, which is related to projective module. This property is also useful tool to determine which module is projective or not. But this is can applied in some non-free module case. Let's see the theorem. Let R be a ring, then taking following equivalence relation. Statement A, P is projective. Statement B, every short exact sequence is split exact. This means for if P is projective, is expressed B, A, direct sum P. And statement C, there is a pre-module F and R module K such that F is size mod P, K direct sum P. If P is really projective module, we can find pre-module F and R module K such that they express this. In prior to prove this statement, let's see the example which is applied this theorem to decide the projective module. For example, if G3 is the G6 module, then this G3 is projective. Why? Let's consider this here. G6 to G and G, and we can understand first G3 is the sub-G module. This is no problem. And note that this is non-free G6 module. As I let's say, this statement to prove this is projective in case of non-pre case. But this is clearly non-pre G6 module. The reason is the definition of the pre-R module. If F is the pre-G6 module, in this case, G6 module, F is isomorphic, the direct sum of copies of G6 module R. So, G3 is, if G3 is pre-R module, this guy is expressed as G6. But this is really false. So G3 is non-pre G6 module. But this is projective. In order to decide this, let's apply theorem C to these examples. If really G3 is a projective module, we can find a pre-module F and R module K such that this relations hold. But note that first the pre-module is G6. In case pre-G6 module, F is G6. G6 itself is a pre-G6 module because the definition of pre-G6 module, there exists identity is basis such that this is G6, and if the linearly independent condition, this is only 0 in the modular sense. So G6 itself is a pre-G6 module. Okay, we find a pre-module, and then this blank is naturally G2. G2 is clearly, we can understand, G2 is a submodule of G6. G2 is G6 submodule. So anyway, G2 is a G6 module. So because we can find pre-module F and R module K and express this, G3 is clearly projective G6 module. Note that again, G3 is non-pre-G6 module. In spite of this non-pre state, we can decide using by this theorem, G3 is projective G6 module. Now let's prove the statement. I prove from A to B, B to C, from B to C, and finally from C to A. First, suppose P is projective. Then consider our claim this exact sequence, predict exact sequence. Then use the theorem. Because P is projective, this when we note that this sequence, we can always find the homomorphism, and this B to PG. So there is the homomorphism such that this commutative relation holds. Then note that if we just find here, our proof is finished. Why? Split exact sequence. In the previous lecture, the equivalence relation of split exact sequence. There is R mod homomorphism. In this case, the letter is different, but this is here. We can find, in this case, G, in this case, H. So, our proof is finished. Now let's see the statement from B to C. Our assumption is every short exact sequence split exact, but this guy P come here, and our claim is we find pre-module F and R module K such that F is isomorphic K direct sum P. But using this split exact sequence, if we use this condition, in particular split exact condition, this isomorphism holds. Then important tip is these guys. Every module P, R module P, we can construct this commutative relation law. So we can find pre-module F, the homomorphism from F to P, this unique homomorphism F to P, by pre-R module relation, commutative relation. So from this basic information, I put the exact sequence. I'll fill in the blank F pre-module. And if we find this is clearly short exact sequence. So if we find K, which is satisfied short exact sequence condition, this is split exact, and this is expressed here. Then what is K? The answer which satisfies short exact sequence is, of course, Fp is G, our assumption. This is surjection. And the answer is corner G. Corner G is subset of F. We know, check this. Corner G is subset of F. Then this around can construct injection map, and this is surjection map. We can construct, because this is subset of, just give the inclusion map, and this is surjection. So this is clearly short exact sequence. That however, by the assumption, this is split exact. So F is isomorphic K direct sum P by split definition of split exact sequence. In order to prove last statement, let's see the following the commutative diagram and use the assumption. There is a pre-module F and R module K such that F is direct sum K to P. So F is clearly pre-module. The pre-module is decomposed as K direct sum P. Then our claim is P is projective module. To prove the claim, we must find the map. Anyway, I don't know, but we can find the map H homomorphism, just finding homomorphism H, then our claim is finished. Because this is clearly the definition of projective module and the commutative relation holds. In this case, F is already used. Anyway, we can just consist of commutative relation. But why construct H? Hint is just using the power of this assumption and assumption. Note that the most important point in this statement, F is pre-module. Why? premodule is, or every premodule is projective module. So anyway, any premodule is given, we can construct homomorphism H prime such that the commutative relation holds from F and this bottom exact sequence. Okay, then this is good hint. Why? We can then we can think we construct the map P BR2A by using this relation. We can naturally give from F to P because F is isomorphic to these guys. From F, in case from F to F, inclusion map is given, naturally given. And then, in case of the inverse case, we can give the projection map. But important thing, anyway, we can give the homomorphism from P to F, and this is already existence by the definition of the property of the premodule. So we can move from P to A. So if just put claim if H is inclusion map and H prime, then this is clearly positive. R, check that this is R module homomorphism. But this is clear because this is also homomorphism. This is also homomorphism. So the composition of the homomorphism map is also homomorphism. So we can check that. And another claim is check that the commutative relation. So just this is H. So because the map H is existence, commutative relation clearly holds. But because specific statement description is your exercise. Just to check this. So if we just do statement, then P is projective module. Now, in case of the injective module case, there are similar lemma to determine to decide injective or not. Let R be the ring and taking following equivalence relation. Statement A, J is injective, B, split exact, and C, J is direct sum member of any module B of which is a submodule. This statement we can easily understand. If J is really injective module, then for any module which contains J. So in some sense, J is a module, submodule of B submodule, R submodule. Okay. So the B is larger set than J. So whenever we choose the B, then there exists N. This is so statement. When compared to statement C, there is a C R module such that B is isomorphic J direct sum C. Then J is injective module. So in this case, statement C is a little difficult because we can just every element to find every module. So this statement is, in some sense, however, this statement is useful to this is not an injective module case. Let's see this example. The subset 0, 2 of G4 is non-injective G module. Well, I will use the instead statement C. I use the statement B. This is also useful. This is every short exit sequence split exact. Then, if we find, if we find the short exact sequence, but this is not split exact, we decide this is J. This J is not a cyclic. This is J is not injective module. So, in this case, our claim, just we show the previous lecture, I construct the short exact sequence G4, and G4 is quotient group, and 0. This is we just show in the previous lecture. 0, A, which leave the exercise, but B over A is 0. Yeah, this is clearly exact sequence or example of the exact sequence, and note that this guy is isomorphic G2. So, and then this is isomorphic to G2. But unfortunately, G4 does not isomorphic G2 over G2, direct sum G2. This is clear. This is isomorphic Klein pool. Every group order 4 is classified Klein 4 group or G4 group, but Klein group is isomorphic G2 direct sum G2, not isomorphic G4. So this, because there exists short exact sequence, this is not split exact. The subset of G4 is non-injective G module. So this tool is useful to decide this is not an injective module. Let's consider this. Let's see the remark. We studied some R module is projective and other is injective. But in this remark, I want to talk about which is injective module but not projective, and which is projective and non-injective, and which is both projective and injective. Let's see these examples. The first example, injective module but not projective module. In example, which I already referred, the answer is rational number over G. So, if Q is G module, then this is clearly injective module because this is the property divisible. Every divisible abelian group, if and only if injective G module. But unfortunately, this is not projective. Why? Clearly, there are some methods to prove just the statement of the projective, but I use alternatively. I introduce some theorems which is applied to this. Theorems is here. If M is R module over PID, principal ideal domain, which is the principal ideal domain. The definition of all of the ideal is the generated form. Okay. Then, if consider in case of G, integer is clearly principal ideal domain. Then, module is projective. If and only if M is pre R module. So if applying this theorem, if Q, assume that if Q is projective and clearly G integer is principal ideal domain, then Q is by this theorem, rational number Q is clearly pre-Z module. Let's consider the definition of the pre-G module. Because this is not expressed as direct sum, just single Q, this basis is only 1. This means the number of the bases is 1. This means the definition of the basis, some element in rational number in Q such that these guys generated whole set. Okay. Then, if consider this here, the definition of cyclic, in other words, rational number is cyclic. This expression is cyclic. Then note that every cyclic group is classified. If this is cyclic, then and definition of cyclic group, every cyclic group is classified integer Gn or G by depending the order. If the group order is finite, this is isomorphic to Gn. The order is infinite, then this is isomorphic integer. Because rational number is clearly infinite, order is infinite, this guy's isomorphic to integer. So this means Q is isomorphic G. But this is clearly contradiction. So our assumption, this is pre-G module is contradiction. So this is the if and only if condition. Q is non-projective module. In case of statement 2, projective module but not injective case, which is measured up? The answer is some example G over G. So G module is projective but clearly not injective. Why? First, verify that G integer G over G module is G is projective G module. G is pre-G module. This is clearly the definition of the pre-module. There exists element identity. This guy is generated in integer and linearly independent. Just basis is identity. But this is non-injective. This I showed already explained. This is non-divisible. It's non-divisible if and only if non-injective. So this guy's G over G in other sense, G module is the non-projective but non-injective case. And last example, which is both projective and injective module. The answer is vector space. we said, and in the definition of the R module, if the ring is division ring, division ring, in this case, what is the division ring? Every non-zero element has a unit. For every element, non-zero element has a unit. This ring is called division ring. And if R is a ring, is division ring, then this is called, the module is called vector space. So if the module is measured of the vector space, this guy is projective and injective module. Why this vector space is both projective and injective? First, check that vector space is pre-module. This is clear because vector space has a basis, and this guy's basis is linearly independent and generated the V. If the vector space bring the V, this guy has a basis, and so each element is linearly independent, and each basis are linearly independent and generated some element V. So this is clearly pre-module. And second case is, in this case, the vector space is projective module. And to check the injectiveness, use this theorem. Every short exact sequence is split exact sequence. In case of the vector space, every short exact sequence is split exact sequence. I will not prove this statement. This is clearly can applied in the vector space. So this is the theorem of injectiveness property, if and only condition. I explained here. Every short exact sequence is split exact. So by two theorems, by these two logic, vector space is both projective and injective module. Okay, I finished in this lecture. The next lecture is the dual module.